Hello everyone, I would like to start today's lecture by discussing the AVR data format. I'm gonna go over the directives, the ROM, how do we place data inside the ROM of an Atmega 328. So previously we had discussed that we have a RAM, that has my GPR, general purpose register, my IO SFR, special function register or special purpose registers, and the SRAM. So this is my data, and this GPR typically communicates with my ALU, and of course data from the ALU will go into the GPR. And we discussed that this is an 8-bit microcontroller. Bit implies data bus is 8 bits. So this is the data bus, 8 bits here, another 8 bits here. Now, what about the instructions? Where do they lie? So the instructions rise in program memory. ROM. So here where we find our LDI R16 2, for example. So place 2 in R16. So the instruction comes and processing happens. If I have another LDI, it's going to be like this, 3, and add R17 R16. So effectively this is where we place our instructions in the ROM. They get out, they place values inside the GPR. The way they do it is of no interest to us right now. Placing 2 in the GPR, 3 in the GPR, adding them together and updating. So all my program resides in the ROM, and the instruction is 16 bits. Instructions are 16 bits, 2 bytes. Whereas the data is just 8 bits. So here I have 16 bits, here I have just 8 bits. So this is the difference between the ROM and the RAM, plus we have the program here, we have our data here. Alright, so now let's talk a little bit about some data representation. So if I want to represent in hexadecimal, I can use LDI R16, 0x99 for example, or I can use LDI R16 $99. Both can be used for hex. Now for binary, I can use the 0B indicator to indicate that it's a binary value. So 1001 0 for example. So we don't need to have any quotations or single quotes. For decimal, I just write the number . So 15 here is in decimal value. Now for ASCII or characters, we know that we have the ASCII table and each character has a value in ASCII. We do something like this: LDI R16 A, and we put those single quotes, or we can do LDI R17, 1. So this is the representation of 1 in ASCII domain, and this is the representation of A in ASCII. This is not decimal 1. So this is not decimal 1. It's actually the character 1. And this is very useful when we're talking about a LCDs and when we want to print out some characters that are in ASCII. Now these are the data representation. Now if I want to talk about the directives, so directives are used by the compiler or the assembler, excuse me, to help writing nice codes. So one of directives are helpers. I can think of them as helpers. They can help me make my code more readable. Helpers make the code more readable. Okay, for example, the first directive is dot equal. So dot equal, it just allows me to name some values. So used for naming variables. Alright, so for example, I can say dot equal x equal 0x25. So now instead I say, usually what I used to do is LDI R16 0x25. Now what I can do is, instead of saying, okay, what's R16? It's my x variable. So I can do something like, let's say for some instructions, LDI R16, x. So what the compiler does is just creating a shortcut for 0x25. Whenever it's going to see x, it will place instead of it 0x25. So the value here is x is actually 0x25. I can do this for whatever, many times. Usually place the directives above our code. For example, I can do something like dot equal. I can say this is my count equals 0x10. My average, well, let's say, I don't know, 0x39, and now we can use them freely with LDIs. So now these are constants. Average. So these are substituted by 10 and 39. I can use as many as I want, and I can use whatever data format I have. We can also use the directives with SFRs or I/O. Consider the I/O register port B. We know that port B is in relative address 0x05. This is the relative address. If you don't know what relative address means, check the previous lecture. So what we need to do is what we usually do with out when we're using port B, we say out 0x05, R16. So this comes here. But 0x05 is just unknown to us. So what we can do is dot equal, and we say port B equal 0x05. Now we can use out port B, R16. So this is much readable than this. So this is why we use dot equal. But how come we used this before? Because we need to include a library. So in this case, I'm gonna add another directive dot include, and the directory is and the library is m328 def.inc. So this file has all the definitions for all the I/O ports. So here and many other information. But for us, for now, let's say this is where the definition of my IOs are, and many other stuff. Okay, so dot include is just like the include you use in your normal programming languages like C++ and Java. So here dot include, and we give the library name, and it has all those port B, port C, port D, the different components that we use using the AVR. So we don't have to actually write this statement because it's already done for us, and this is why we have done this before in the previous lecture. So also another directive is .org. So .org, which is origin of code, so tells the assembler where to place data, instructions in ROM. For example, say .org 0x100, and then I said LDI R16 say 0x20. So what happens is this is the program memory and the ROM, and it will start at 0x100 placing those instructions. So this is the ROM. So from here, and this will be empty or containing other codes. So .origin tells the assembler where to place instruction inside the ROM. So one golden rule that we should remember is that directives are not instructions. They are helpers for us to write a nice code, to place some stuff inside the memory, to include some library functions inside our code. So they are used for many stuff that we can do using when writing a code, but they are not instructions. So now if I want to change gear a little bit and talk about the ROM, so or the process of writing a code. So first I'm gonna go ahead and talk about structure of a code. So structure of assembly program. So usually start with a .include, and we are using the m328def.inc. This is our library file, contains all the definition. Then we can have some .equals here for our variables if we want. And then the way we write the code is that we have a label, okay, the mnemonic, operands, and then we have the comment. So for example, I can say start, this is the start of my code, let's say LDI, this is the mnemonic, and then I'll take R16 0x20, this is the operands, and then the comment, I will say loading 0x20 into R16. So this is the way we write the code usually. So for this, after writing a code, so let's say we wrote a code, what will happen? So usually we have the following. We have an editor program, So this is where code is written. Then we have the assembler. So this is where it checks the file. Usually we write here with my file .asm, so .assembly, and from this the assembler will generate many files. So it is .eep file, .hex file. We have also .map. We have .list, and then the last one is .object. So these two, this goes to the EEPROM, and this goes to the program memory of microcontroller. So when we say we program the microcontroller, we're actually talking about these two. Put the EEP file in the EEPROM and the hex file in the program memory of the microcontroller. Now, if I want to say, okay, so what is the .asm file? This is the assembly code, LDI and whatever. Hex is the machine language of my assembly code. We're gonna talk more about how to translate from assembly to hex. It's .eep is the EEPROM file. We have the .map, and this file is used to show labels. And their definitions. And .list, which is binary and source code. And this can be optional. So assembly is we write our code in the editor. .asm is saved, then we hit assemble. We have all these files. The hex file is the machine language which is used to program the microcontroller. The EEPROM if you're using some external programmable memory, and we have some values that we want to save in it. The map shows the labels and definitions, all these labels and the equal and directive. .list shows the binary source code, the binary and source code side to side, which is optional. It's not always there unless you choose it. So now, after we discussed the process of going into the editor and the assembler and generating all these files, let's talk about the program memory and the code and how do we program the memory with the hex file. So as I said, let's talk about ROM. So for the program memory, the ROM, we have this instruction LDI, and then we will have add and several instructions. So first of all, who's responsible for choosing which instruction? There is a counter called PC. It's called program counter, and what the program counter does, it points to the address of the instruction we execute next. So PC points here, this means the next instruction to be executed is LDI. Alright, so PC is the driver for our code. So we say we execute the first one this one first, and then this, and then that. Who's telling this the processor to do this is the program counter. So when the program counter points to LDI, actually it fetches LDI, and then it goes in the same clock cycle, it goes to point here, just telling us that when we finish LDI we will be executing add. Okay, so the program counter is the main driver of our instructions. So if I want to know the size of the ROM, so what is the size of the ROM? What do I need? So first, I know for a fact that the instructions are 2 bytes. So instructions are 2 bytes. So this means if I draw the ROM bigger here, this is the ROM. This is 16 bits or 2 bytes. Now we're gonna use word addressing. So what do we mean by word addressing? This means this will be location 0, this will be location 1, this will be location 2. The other way of addressing is byte addressing, where we say 0, 2, 4, since we're counting the bytes, but here is not the case. With word addressing, we count the words. So what words I'm talking about? The words, I mean by them the instructions. So this is what I'm dealing with. I'm counting the instructions. All right. So the bigger the PC is, the bigger the memory is. So for example, if I have 14 bits for PC, and we know that the instruction is 2 bytes, what is the size of the ROM in bytes? So first, so the PC is 2 power 14 locations minus 1. So 2 power 14 times 2 bytes. If PC is 14 bits, then I have 2 power 14 is the number of locations that we count. So we have from 0 to 2 power 14 if PC is 14 bits. And this gives me 2 power 10 is actually k, 1k. So we can write this by 2 power 5, since I multiply this, times 2 power 10 bytes. And this will be equal to 32 kilobytes. So if I have 14 bits, I have times 2 bytes, then I have a memory of 32 kilobytes. Now, if I want to give the problem in another way, so let's say I have a 64 kilobyte ROM. Given a 64 kilobyte ROM, what is the size of PC in bits? So let's say I have 64 kilobytes. So I know that the ROM has 2 bytes per location. So first, to have the number of locations, so number of locations in ROM is 64 kilobytes over 2 bytes. This will give 32k, which is equal to 2 power 5 times 2 power 10 equal to 2 power 15, implies PC is equal 15 bits. So this is how we can go from having a size of the ROM to getting the PC, and or vice versa. If I have 15 bits, I just take the powers of 2 and then multiply it by 2 bytes to account for the size. Now for the Atmega 328, which is the microcontroller we are using, it has size of the ROM, the size of ROM, if you look at the data sheet, it's going to be 32K. This means the address goes from 0x12345 to 0x03. So how come we reach this address? This is because if I look at the PC for a 32 kilobyte ROM is as follows. So we have 32 kilobyte, I divide it by 2 bytes, this will give me 16K, implies I have 2 power 14, okay, and implies PC is equal 14 bits. So if I took 14 bits, I can count them here, 1 2 3 4 1 2 3 4 1 2 3 4. This is 12 bits, 1 1, so this is 14 bits. So this is the maximum or the last address in the ROM. So if I take the ROM of the Atmega 328, it will start from 0x0000 and end up with 0x3123. So this is the last address. This is the last place I can place any code. Now, since the AVR microcontrollers come in different ROM sizes, I don't have to always redesign the PC to accommodate to all these ROM sizes. So, for example, Atmega 8 has 8K ROM. We know that the Atmega 328 has 32K ROM, and we have, for example, the Atmega 256 has 256K ROM. So in order to accommodate for all of these, what was done is that the architecture gives PC the maximum allowable amount of bits. So for a program memory, whatever the size it is, for a ROM, the size of the PC is always 22 bits, and this is 2 bytes. So size of PC is always 22 bits. So this gives us a maximum of capacity of how much? So given PC equal 22 bits, what is the maximum capacity of ROM that can be handled? So here we say, okay, since we have 22 bits, it's going to be 2 power 22 times 2 bytes. So this means we have 2 power 2 times 2 times 2 power 20 bytes. So it's going to be 8 megabytes, or we can say 4 mega words. And remember, the word is 16 bits, so this is 16 bits or 2 bytes. So this is the maximum allowable memory inside any Atmega microcontroller is 8 megabytes. We cannot go above the supported length because the PC is limited for 22 bits. Otherwise, we need to redo the whole architecture. So the architecture of Atmega microcontrollers has PC as 22 bits by default, even if it's 8K or 256K. So you might ask, what we'll do with the other bits? They are left unused. So we will see in the examples later in this lecture that for 32K we don't use the whole 22 bits, we just use for this 14 bits So the left are zeros. So we don't care about them because they will not be accessed. So now let's talk about how do we actually place values inside the ROM. So changing, converting to machine language. So let's take the first instruction. So let's say we have LDI, let's say R17 0x34. So first we need to know the layout of this instruction in binary. So the layout is going to be as follows. Like this. Remember, this is 16 bits. So we have the first 4 bits are always 1110, and then we have K, 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 and then we have D, 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 and then we have another K, 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 K. So the K is from here. So the K, this is the K. It goes like this and like this. And the D is actually here. Remember that LDI has RD, comma, K. So now if I want to translate this to binary, first I notice that I only have 4 bits for D. So this limits me for 16 values only. So now you see why LDI supports D between 16 and 31. However, 16 is more than these 4 bits. So what we do to get the real D, so D will be 16, or D new will be 16 minus D. So in this case, if I have D minus 16. So in this case, if I have 17 as my D minus 16, this will be 1. So this what will go into this D. The K is 8 bits. We put the least significant bits here and the most significant bits there. So now what will happen is that we will have 1110, which is, this is the opcode, or this is what tells us this is an LDI instruction. Then this 3 will go here. So we have 0, 0, 1, 1. The D will go there, 0, 0, 0, 1. And then the rest of the K, which is the 4, which will be 0, 1, 0, 0. So now if I want to write it in hex, it will be 0xe314. So this will go inside the ROM. This is the machine language I'm talking about. This is what the processor will read. It will not read LDI R170x34. It will actually read E314 and will translate it to LDI and will place 34 in R17. So always remember, with LDI we need to subtract D from the value from 16. So let's take another example to calculate D. So if you have LDI R20 0x20, so here the D new will be 20 minus 16, it's going to be equal to 4, and now the machine language will be, I'll do it here, it will be the same, 1110. This stays fixed. Now I have 2 instead of 3, so 0, 0, 1, 0. Then I need to put 4, 0, 1, 0, 0, and then the zeros here. So if I want to just emphasize, we have here this, and this makes K, this makes D, but I need to add to it 16 to get the 20, so 4 plus 16, 20, and this tells me it's LDI. This is the opcode. So this is the first instruction that we're gonna take, and this tells us how to do we transform from LDI to machine language. Or if I take another instruction, which is the add instruction, remember the add takes RD and RR. If we take a look at the layout of this instruction, it's going to take 0, 0, 0, 0 first, 1, 1, R, D, then I have these, then I have R's. So this is 16 bits as usual. So the first, this tells me that this is an add instruction. This is the opcode. Now, the way its layout is that D, this is, we have 5 bits for D, 5 bits for D and R. So now you understand why with add we can access the whole GPRs. D, R, 31. So let's take an example. Let's say I need to have add R, let's say R16 and R17. So if I want to write this in a machine language, so first I copy down the opcode or the thing that tells me that this is an add, and then so R, let's put this, R is this guy here, it's going to be 17, so in binary it's going to be 1 0 0 0 1. R is 16, it's going to be 1 0 0 0 0. Okay, so first this is D. Okay, so R has 1 here, so I'm going to place this one here. I'm going to put R in red, and I'm going to put D in blue. So we place the first one here. Okay, this is for R. Then we have the one for the D. Then we continue with the D, and then we continue with the R. So you see, this makes R and this makes D. Let's write this in. This makes D. So now if I want to write it in hexadecimal, so this will be 0x, 0x, this will be 0, this will be F, this will be 0, 1. So this is the translation of add in here. So we must remember that the most significant bit, this guy, will go here, and the other most significant bit here will go into there. I'm not gonna write it so it will not be messy. Now, so this is the add instruction. Now let's talk about a different type of instructions, which is the SDS and the LDS. So the previous instructions were 16 bits. SDS is a 32-bit instruction. So this means it takes 2 places in memory. So if I want to place an SDS, so let's say this is add. If I want to place an SDS, it will take 2 places in memory. So this will be 0, this will be 1, this will be 2, and then 3. We have LDI, which is also, this is 16 bits. This is 16 bits. And SDS takes 32 locations, 32 bits. So I'll go ahead and write, so we have SDS, say K, R, K, or RR, for example. So now, if I have, I write it like this, so we have 1 0 0 1, we have 0 0 0 1 R, and then we have R R R R zeros. This tells me that I need to fetch the other instructions, and then I have the K's. So remember, K is 16 bits, right? because what SDS does, it fetches from the RAM and places in RR. So let's say I have SDS 0x 305 comma R17. So now, how can I translate this to binary? So now I'm gonna write the same thing again. So first I'm gonna stick with the operational code, which tells me that this is an SDS. Now I write the R. R in this case is 17, which is 10001. So now I'm gonna write the R in blue. It's going to be, sorry, this is, there's I added a 0 here. So we have 001, and then I add R, the first one, this is 1, and then 0001. So this is R. And then, so let me just, this is, I added just a 0 here. So, and then I have the normal zeros. Down here I have this address. So this address, I'm going to write in red, will be placed here. So now I have, of course, I have zeros because it's 0305, and then I have 0011, then I have the zeros, and then I have the 5. Okay, so if I want to represent this in a ROM, we have something like this, and these two will go inside the ROM like this. So the SDS takes 2 locations in the ROM. It has 32 bits, and of course the range of K here is 16 bits, which means can go from 0 K to 2 power 16 minus 1, which is 65535, which is 2 power 16 minus 1, all location in RAM. Okay, so the same situation happens for LDS. It's also like SDS. So LDS RD, K, and remember LDS reads from memory location into RD. The layout for changing into binary, again, it is a 32-bit instruction. So we have 1001, and then 000 D, and I have 4 Ds. I have also zeros. Then I have the 16 Ks. Remember, with the K we start here with the least significant bit, and here the most significant bit. Now another instruction is, I'm not going to do an example of this because it's the same as SDS. So another example is in RD, A. So remember, A is the relative address. So if I present the layout again, it's going to be as follows. We have 1011, this is the operational code, 0, then A, D, and we have D, and then we have A. So if I take an example in R18 pin B, now first of all I need to look out what pin B is. So if I go ahead and check what pin B, I can check the SFR. So let's say this is the IO SFR. We notice that we have 2 addresses for this. This is pin B, and it has 03, and the address is here 23, 0x23. So actually the real address is 23, the relative address is 03. So this is not clear. Let me write it in a more clear way. So this is 0x03. Okay. So now to translate this into binary, first I place down the opcode 0. Then so A in this case is 03. So this means I don't have what do you call it? I don't have 8 bits for it. I have 1, 2, 3, 4, 5, 6 bits. So I'm gonna write 1, 1, 0, 0. These are 4 bits and 2 more bits. So now I have 6 bits. 6 bits for A. 1, 2, 3, 4, 5, 6. And D is 5 bits. We know D is 18, so let me write it in a different color. D will be, which is 1, 0, 0, 1, 0. So now I start with A. I'm going to write it with the red color, so with the blue color. So I'm going to write 2 zeros. So I wrote this. And then I have D. It's going to be 1. And then 0, 0, 1, 0. And then I'm going to continue with this part of A, which is 0, 0, 1, 1. And to write it in hex, of course, this is 0xb 1, 2, 3. So this is an example of translating an in instruction to hexadecimal into binary. Of course, out has similar operations. I'm gonna just give the layout of out. I'm not gonna do an example about out. So this is out. It's gonna take A and RR. It's also a 16-bit instruction, and we'll have 1011 and 1 A R R R, and then we have A. Of course, D goes between 0 and 31, and A goes between 0 and 63. Now the last instruction we're gonna go into is the jump instruction. Jump instruction, and we usually take jump and takes a label, and this label is, of course, it should be 22 bits. Why? Because when we do a jump, let me explain a little bit about jump. So let's say I'm somewhere here and I say jump exit, and exit will be somewhere here. So let's say, and here we have instruction. So let's say the address is, let me write the address 0x, let's say 0532, and this is 0x, it's going to be 0AF4. Now these are just random addresses. So jump, when I reach this instruction, it's gonna go like this. So this is the ROM, of course, since we are dealing with the ROM. And remember that PC is 22 bits. Okay, we are using only 14 bits of it. Okay, so if I go ahead and check the binary representation of jump, it's going to be 1001, and then we have 010 K. I'm gonna write directly the subscript of it. So this is K21, and then I have K20, K19, K18, K17, and then 110, K16, and I go ahead and do K15 till K0. This is 16 bits. Okay, so now if I want to transform this instruction to machine language, first of all I need to know where exit is. Exit is at this address. So first I write this address in binary. So let's say exit is going to be 1, 2, 3, 4, and again 1, 0, 1, 0, 1, 1, 1, 1, and 0, 1, 0, 0. These are 16 bits, right? However, I have 22 bits, so I need to add 5 more bits. 1, 2, 3, 4, 5. To have, these are 5 bits. Excuse me, 6 bits, so I have 22 bits. Okay, so this will be K21 and this will be K0. So now, if I want to write this instruction, this is a 32-bit instruction, of course. So the first one is going to be like this. This will be 1, 0, 0, 1, 0, 1, 0. Now I need to write K20. So K20 is 0, K21, K20 is also 0, 19, 19, 18. So 21, 20, 19, 18. This is K17. It's going to be also 0. Then I go ahead with the 1, 1, 0, and then also K16 is 0. So I write K16. This is K16. Now I go ahead and continue, and just do something like this, and then I continue with the 16 bits here. So it's going to be 0, 0, 0, 0, then 1, 0, 1, 0, okay, 1, 1, 1, 1, and we have 0, 1, 0, 0. So this is the binary representation of jump. We notice that the green writing is just the opcode, and then we have the address in red, and we start from, this is K21 and until we reach K0, and this is K15, which is the rest of the 16 bits. So the last topic I want to talk about is placing values inside ROM, placing hex instructions in ROM. So here we have two methodologies. So let's say this is the 16 bits of the ROM. So we have something called Little Endian, which means high address, high byte goes to high address, and low byte goes to low address. I'm going to explain what this, and this is what the AVR at Mega uses. So let's say I have, for example, an instruction called, let's say LDI. The first one we did is LDI R17 0x 34. So this will be 0x E314. So you might see that we have here the low byte, and this is the high byte. So if you consider ROM like this and we divide it to high address, so this is 0, then we have 1 and 2. So let's say this is the low address and this is the high address. So what we do is actually write the 14 here and the E3 here. Of course, this is hex. Okay. So let's say we have the jump instruction. So the jump instruction is as follows. It has jump exit, for example. We have the binary representation or the hexadecimal is going to be 0x, it's going to be 4C, and the next one will be 0x0AF4. So now if I want, this is just LDI. Now if I want to have the jump, it's going to occupy both 1 and 2. So I write first the low range, it's going to be 0x0C, and here we have 0x94, and the next one will be 0x0A, 0xF4. So you notice this is both jump. The processor of the microcontroller will know that when he sees the opcode of this, that he needs to fetch two instructions, not just two places, not two instructions, two places for the same instruction, not just one place for the LDI. So placing values in the ROM, just we need to abide by that the low address has the low byte and the high address has the high byte. The other way that we're not gonna use, that's not being used, is the big endian. So big endian is as follows. It goes with high byte, will have low address, and low byte will have high address, not used with Atmega. So we're not gonna go into details about this. So this concludes this lecture. We discussed how to place values inside the ROM, how to compile, how to assemble a program, and have the machine language and some of the directives.